Welcome to this presentation on cases to objects and relations and beyond, which is a talk about object-centric processes and object-centric process mining. I gave this talk at the Objects from A to Z workshop at the BPM Conference 2023 in Utrecht. My name is Dirk Valand. I'm an associate professor in multidimensional process analytics at the TU Eindhoven. And I want to use this talk to give you an overview on the field of object-centric processes, the foundations of the concepts of object-centric processes, and what you can do with them, also in use cases that at the moment you're not even aware of that exist. Object-centric processes took center stage for a wider audience at the Cellosphere presentation 2022, when the Processphere product was introduced, which showed this beautiful visualizations of processes in this metro-style map, showing how multiple different objects together interact and participate in a joint process execution. Now, why was showing this picture, this kind of models, so impactful to the wider audience of process analysts? For that, we have to take a step back and look at what we're analyzing. We're analyzing processes in the real world, which are controlled and supported by information systems, IT systems, and we can use these systems to record event data about the process executions. And we can use this data to analyze our processes and to construct, for example, process models that describe the processes in the real world, or even construct models that prescribe how the system should operate. Now, in reality, there's not just one process, but reality consists of multiple processes that are run by actors who handle documents and items, who interact with machines and are part of multiple organizations. And this complexity is managed by a lot of stakeholders who have to communicate and align with each other in order to get operations to run smoothly. And process models are an actionable means of communication here that help all the different stakeholders involved in the real world to agree on how to proceed by relating their own goals and actions to those of other participants. And the models help to talk about what others see in a process. So that's why a model that describes this reality better is likely a better means of communication. So that's what we're after. And this is what these object-centric process models do. This is what helps them, what makes them an effective tool. Now, how did we arrive here? There was a lot of research going into object-centric processes before that. So, for example, I presented this model at the Process Mining Summer School in the same year in the summer before Cellosphere, and you see a lot of similarities. So the research was moving in this direction already for quite a long time, and I wasn't the first to look at object-centric process mining. If we look at the timeline, how we got to object-centric process mining, then there was before that, for example, the work by Alessandro Berti on object-centric process mining. He had the first implementation of an object-centric process mining algorithm and the tool. There was a tool for object-centric process mining by Mehrwerk process mining, that already existed. And there's my own work on event knowledge graphs that I will talk about later. And before that even, there were other works like information system modeling by Artem Poliviani and Jan-Martijn van der Werf. And even earlier, we had a wave of artifact-centric process modeling and process mining. And there's lots of similarities in these ideas of modeling processes and mining processes that led to the development of object-centric process mining. And these ideas were developed in 2010, 2011, so more than 10 years ago. So how come that there was so much time taken from these first ideas to a easy-to-use idea that made it into a commercial product, that in between we were still using classical case-centric process modeling and process mining ideas? So I want to reflect on this a bit, how we got from cases to objects and how the path we took to get to the idea of object-centric process mining. Then I want to look into object-centric process mining itself. How does that work? We'll also look under the hood. And then I want to go beyond. I want to look at relations between objects and completely different kinds of use cases that at the moment you cannot imagine, but that are possible with this concept of object-centric process mining. So to introduce you to this idea of how different processes, how we thought about modeling processes 10 years ago or even 20 years ago, I have to introduce a short example. We have an online store where we have customers placing orders at this online store, and you know that if the products are different warehouses, they get packaged into multiple different packages. Now, there's a delivery service provider that is taking packages in, and it will group packages from different orders into the same delivery tour. Then the first package arrives at the blue customer. The red customer is not at home, so the package goes into another delivery tour the next day, is joined by the second package. The red customer receives their package, and the blue customer rejects the package. Maybe it was damaged. So what we see here is multiple processes that are interacting. Then there's not a single way of describing this whole interaction as a sequence, as a case, as we do in, for example, classical process mining or process modeling. Instead, we have to model this as multiple processes that are executed in parallel. If we try to force the data into a case and to extract the data along the sequences of a case, what happens is we take the events from which are stored in a relational database that model these many-to-many relations between the orders and deliveries. And then in order to extract the cases for the events for each of the cases, I pick one object that is leading, for example, the order 1 object. I take all the events of the deliveries that are connected to the object, so from delivery 5 and delivery 6. I extract the events and order them in time. And then I get all the events from the different objects in a sequence. And I have to do this for every case. So I also have to do this for the second order, which also is related to delivery 5 and delivery 6, and I extract also these events. And what you then see is that we have events which are extracted twice because they are part of an object that's related to two different orders. So they get extracted twice into two different cases. We get event duplication that's called convergence. But we also get false dependencies. So we see here in the second case that delivery 6 was followed by an event in order 2, then again followed by an event in delivery 6. But we do not have a structural relation between these two objects. So that's a false dependency, which we call divergence. And this happens because we denormalized the underlying data structure. If we apply event log extraction to real-world data, then the false dependencies, divergence, is a huge problem, because in this data we will get primarily wrong edges, which are false, which do not have a correct underlying structural relation between objects. And these edges are the majority of the edges, and they're also often in frequency the strongest edges, so we can't even filter them out. That makes process models that come from such processes with multiple objects that are related, or multiple processes that are related, but squeezed through the view of a single case, inherently wrong. We can't use them if we want to understand the processes. So what did we do instead? We said, okay, if we have multiple objects, then we have a data model, which describes we have an order and we have deliveries, and they're in an M-to-N relation. And the idea of artifact-centric process modeling was to say, okay, let's describe for each of the objects that exist their own life cycle, their own local process. So we have process executions here for order 1 and order 2. These are two local cases for each of the orders. And we also have the process executions of the deliveries, from delivery 5 and delivery 6 later on. And these process executions, they interact through message exchanges. So asynchronous communication, the first package gets passed from the first order, where it's split into multiple packages, and that package then ends in the first delivery. And as the second package that gets split, that gets passed to the second delivery. Both deliveries receive packages from the other order or from a previous delivery tour. So we have interacting cases that are synchronized through message exchanges. We can model this. We can create a process model of this. This is the model of proclets that was already proposed by Will van der Aal's in 2000, so over 20 years ago. And the idea is that in this model, you have models for each of the processes, for the order and the delivery. And then you model the interaction as a message channel, from splitting the package into multiple packages, into loading the packages into the delivery tour. And the channels are annotated with cardinality constraints about how many messages the order has to produce and how many messages the delivery tour has to receive in order to communicate. So split here has to create at least one package, can be more, and the delivery tour here has to receive 0 or more packages to start. That's the model. Now, based on this idea, we developed artifact-centric process mining. Artifact-centric process mining defined a data model around a relational database that defines objects, activities of these objects, so which activity is part of which object, and relations between objects. From the objects and the activities, we extracted a log per object, so the cases that you've seen before per object, and we can discover a process model or a lifecycle model per object. From the relations, we extract which two cases of two different objects are related, take the events of these two cases into a merged log, ordered events by time, and then identify where activities of two different processes interact and add these interactions to the process model. So we get this process model where object life cycles are connected through message exchange. Now, we implemented this in prototypes and PROM over 10 years ago, and this concept worked. It allowed for discovering such models from real-life data, but it didn't scale. The moment we got to analyzing object life cycles over multiple steps with many interactions, we got, again, say, dependency spaghetti, if you want. And these are not false edges like we had in the previous directly follows graph. These edges are all correct, but it makes it very difficult to understand what's going on. So relations as first-class citizens in a model are too complicated to understand and to reason about. So we then turned to some advice from Carl-Adam-Petri, the inventor of Petri nets, and I got the opportunity to talk to Carl-Adam-Petri some time ago in Berlin while I was a PhD student, and Carl-Adam-Petri explained to me what a Petri net is. And he said, when you think of a Petri net, you don't begin with the places or the transitions, so the modeling constructs that you draw on paper, but you think of the tokens that are managed by the Petri net, so the things that the model is supposed to describe. And a token, you should imagine, is an object that is going through the universe and moves through the universe. And if it moves through the universe, if it doesn't meet anything in between, it will remain in the state and the condition it is in. But if two different objects meet, then you can have an event from the interaction of these two objects. Let's get a transition that fires. But if two objects don't meet, then you don't have a spontaneous change in the state. And this leads to the idea that everything in the universe, at least if you want to model it from this angle, it arrives from interacting and intersecting paths of objects that meet and synchronize in various moments. So how could we apply this to the problem of modeling complex processes over multiple data objects? We can also look at data modeling here, because we know if we have a data model where we have an M-to-N relation between the order and the delivery, if we want to implement this data model, we need to reify the relation between these two concepts into another relation, into another concept, the package, which then models the one-to-N and the N-to-1 relation, so that we get our data into second normal form of the database. So let's apply the same reasoning, the same idea to process modeling, where First, we had the order and the delivery toward which we were communicating with M2N interactions. Let's introduce a model for the concept that sits in the middle, the package. So this also gets a model, and we're going to place it here inside. And this is how this looks like. So now we don't have message channels that exchange messages, but instead we have two objects synchronizing their steps. When the order is reaching the step of packing the order, splitting the order into multiple packages, then package objects get created. And these two synchronize by, say, essentially merging these two transitions into a single one, into a single action. But the specialty is that we're not just merging one order in one package. We have a one-to-N relation. There can be multiple packages over here that participate. So that's why the synchronization, the merge, is dynamic at the moment in the situation where you know how many packages you're going to have. And this applies to all the other steps as well. So how does this look like if we look at the behavior, the executions, the traces? This is how this looks like. You have, as before, the cases, the executions for the individual objects, the orders, the deliveries. But we now also have packages as objects. They also have their own path in which hold the events that describe what happened to the package. And when we are splitting our first order into multiple packages, then we have the events of splitting the package in the order, but we also have the events of creating these packages. And they synchronize in one joint event. This is one event where they all participate, where the packing the order creates these two packages. And I can do this for all the other events as well, where the different objects synchronize. So now I have a view on the world where I have just object paths and synchronizations. And I can model this synchronization, of course, also in other models. So the object-centric Petri nets that have been proposed later fuse this transition that is doing two things at the same time, right? Two different objects into a single transition in which two objects participate. And we indicate that there's multiple objects participating on one side by a different edge, right? So a thick edge that says, okay, there's multiple objects coming in and multiple objects going out of this transition of the blue kind. Now, what was still missing in this view towards object-centric process mining is how do we now get event data into this shape? Because so far we had data in relational databases, and they don't look like that at all. Here came the final crucial idea of Wilf van der Aalst of introducing object-centric event logs, which was the start of object-centric process mining, which is what we're going to look at next. Now, in order to introduce you to object-centric process mining and the ideas, I'm going to introduce another example. It's again a retailer. So we have here two orders that are being placed by customers that hold certain items, like first order has two items X, one item Y. The second order has one item X, one item Y. And the retailer orders the products from suppliers. So there's a supplier order for 3 items X and another supplier order for 1 item Y. So you already notice here's a small mistake, which we're going to fix in a moment. And after these orders have been placed, multiple things can happen in parallel. We can create invoices for the two orders, one for order 1 and one for order 2. And we'll also receive the items from the supplier order and unpack them into individual objects. We can also update the supplier order into an order that now has 2 items Y, which also means we need to update the invoice. And at some point, we also receive the products Y1 and Y2 from the second order. And only then, when the products from the second supplier order arrived, I can actually pack my order for shipment by taking X1, X2, and Y1 into the first order and shipping it. Now, there might be a rule in place that a customer can only get the second shipment if they've paid their invoices. So if we assume here this was the same customer that placed both orders, we first have to wait for the payment that clears both invoices before the second order is shipped with the remaining products. And you already see here, it's hopeless to just even try to describe that in a single case. But you see that it is a lot of very clearly describable interactions of different objects. So how could we record that in event data? This is how this looks like. This is an object-centric event log here on the right, showing the first 4 events of creating the 2 orders and the 2 supplier orders. And you see here that my event log has, as before, an activity column and has a timestamp column, but we don't have a single case identifier column anymore. Instead, we have multiple columns that hold the different object identifiers. And we have here the object identifiers for the order, holding the values for O1 and O2, and the supplier order for A and B, and it's in different columns. We can also have objects related to each other in a single event. So when the invoice gets created for the second order, invoice I2, it's related to order O2, then I record the relation inside the event. So this is the crucial step in the idea towards object-centric process mining, where we no longer have relations as first-class citizens. We only have objects, their path, and the synchronization in joint steps. That means the relation is part of the event. So here in the event, we see order 2 and invoice 2 are related. And this relation can be also a one-to-many relation. When we receive the products from the supplier order, we receive multiple items, x1, x2, x3. We have multiple identifiers recorded here in the item column. And we see the one-to-n relation between A and multiple items. So this is an object-centric event log, and if we continue the execution, we'll get more events of this kind until we have our full object-centric event log, where we have for each of the object types its own column that holds the identifiers. And now this enables object-centric process discovery in a very, very simple way. The idea is super simple. We extract per column, per object, the log for that column, and then discover the model. So if we take the order column, we take the events for each of the orders. So for order 1, we take event E1, E18, E27, and E28, order them in time. We have the case, the local case for order 1, and we do the same for order 2. And if we then put this into our favorite process discovery algorithm, we get such a Petri net, for example. It describes the behavior of this order. We can do this for all the other object types as well. So we get now 5 process models for the 5 object types that we have in our data. The next step is to discover the synchronization between the objects. We see that if we have an activity that is participating in 2 different objects, for here in orders and invoices, then we also have the identifiers that occur in the events related to these activities. So we can extract the synchronizations per activity. We identify the relation that's recorded in this activity, and we see that first of all, orders and invoices synchronize. So we can add the synchronization edge, meaning when an order executes the create invoice activity, then we also execute the create invoice activity and the invoice, so they both happen together. And from the pairs of relations that we see, we have O2 I2 and O1 I1, so it's a one-to-one relation. We also know the cardinality of the synchronization. It's always one order synchronizing with one invoice. Whereas for received supplier order, for example, we will have one order synchronizing with multiple items. So if we do this for all the activities, then this is the model that we get. This is a synchronous proclet model that we discovered using object-centric process discovery, and we see here also the one-to-n relation, right? Packing the shipment. One order packs multiple items into the shipment, and here receiving the supplier order, one supplier receives multiple items. Now, if you look at this model very closely, then you will see none of the object life cycles have parallelism or concurrency. That means I actually can get rid of these places and just model local directly follows graphs for each of the different objects and their synchronization. Or if you don't like the synchronization edges, then you can also fuse these activity nodes into a single node, and you can get this very nice, beautiful metro-style map where you have the create invoice activity in which orders and invoices are participating. And by the object type, I'm now able to distinguish choice and parallelism. So here after create invoice, there's the choice between updating the supplier order or packing the shipment, whereas the invoices continue in parallel from the orders. So that's the idea of object-centric process discovery. It's very, very simple, and things that are simple also very powerful. But let's also have a look at the method. So we had artifact-centric process mining as a method. Now in object-centric process mining, things are much simpler. You have the object-centric event log, where per object we extract a log and then discover the model. And the activities hold the relations. So we, from the activities, just synchronize the activities in our model. So also the procedure for discovering the model is simpler. And again, simpler is better. And this enables a much better process analysis. So here we have a prototype. This was developed by Jan Nicholas Adams, object-centric process insights that allows to discover object-centric Petri nets, one way of modeling these processes. But what it also does, and it's very interesting, is it defines now new process variants. Process variants are a very important tool in process mining, where it allows us to distinguish the very different ways of how a process is executed. And now with with an object-centric view on the data, we can define our variants also considering the object dimension, how many objects are participating in this order, 2 items, 2 deliveries, and also their partial order over time. So how these different objects synchronize over time. So that gives us an idea that there's very different ways of how, for example, here always 1 order, 2 items, 2 deliveries synchronize. And if I have more objects, I have a different variant. Can also do better performance analysis. Classically, when we analyze the performance, we can measure the waiting time, the service time, and the sojourn time of an activity by looking at the start and the end time and the time before the preceding activity finished. Now, in an object-centric view, if I'm here conducting a test in a medical setting, and there was a preparation activity, and I know these samples that are being taken here belong to this test, so there's a structural relation between these two, then I can define performance measures that take into account this relation between objects, and I can better analyze the relation between preparing the test and conducting the test, right? By jumping over the events that are say underneath of the objects that are underneath, but I can also analyze how much time it takes for all the individual objects to arrive until I can conduct the test. Now, understanding how this works requires a deeper look under the hood of object-centric process mining. This is what we're going to do now. So I will now take you into the data model that is being used for calculating in object-centric process mining. And once I've done this, we can look at use cases that use the same data model, but that go far beyond object-centric. All object-centric analysis uses a graph-based model underneath. It's not always stored in a way that the user can access it. Some approaches do it, but there's always a graph-based model. And the idea is that events are stored as nodes. So if I illustrate this on the small example, for the 5 events that you see in the bottom right table, I'm creating 5 event nodes. And each of these event nodes carries all the properties of the event records from my object-centric event log. And it has the activity, it has the timestamp, and so on. Next, I create object nodes, or entity nodes, as I call them, because we will later on see that we can track more over time than just business objects that are managed in a process. So for example, I have here for the event 30, payment P1 is mentioned as an object. So I know the object P1 exists from the data, so I can create this object node for the payment and relate it to the event with an edge. So now I know this event E30 is working on object P1 with this correlated to edge. There's 2 more identifiers in E30, I1 and I2. So I also create the object nodes for the invoices. And I do this for all the events. Then I obtain this graph that shows me how all the events in my data relate to all the objects in my data. Now we add the time perspective. For each object, each individual object, we take all the events that are linked to the object, we order them in time, and then for any two events that follow each other directly, we add an edge, a directly follows edge, that describes E18 was directly followed by E30 from the perspective of invoice I1. So we also add properties to the edge that says, okay, this was for I1. If I do this for all my objects, then I get multiple local paths for each of the objects that run in parallel and that synchronize in a joint event, as you've seen before. And as I said, there are differences in approaches. Some use this as a conceptual model and have a computational data structure inside. You can some use relational data stores to model this, or you can also use a graph database. I'm using a graph database, and I'm really materializing this kind of graph in the graph database, which allows to do much more than just simple computations for object-centric process mining. I will show that in a moment. But because I store it in a graph database and I make it accessible to manipulation, I call this an event knowledge graph. So here's how our graph for the data looks like that I've showed you before. It's you see all the different paths of the objects that are flowing over time, and they're partially ordered, right? So not all events are related to each other. For example, we see the two supplier orders are completely independent of each other, whereas the order depends on the supplier order via the items that arrive. That now also allows us to model and analyze this performance, that idea that we've seen before. Right? So now I can analyze how much time it takes for this pack shipment activity to complete, and when essentially it started the batching for this pack shipment activity, and what was the last activity preceding event or item that was needed in order to do the pack shipment activity. And it gives me a completely new idea of where the bottlenecks are in my process, for example, related to batching. In this graph view, in this knowledge graph view, I can also do process discovery within the graph. So if I take the idea of the event knowledge graph as a model that I can enrich in it for more information about the process, then I can extend the graph with a process layer where for the events that you've seen before, we now aggregate events into activity nodes. So the two create order events are aggregated into a create order activity, so in the create invoice nodes. And then I can also aggregate the directly follows edges between my events into a directly follows edge between activities. So by doing this, I can discover a process model that sits on top of the events, and all the dependencies that I see in my process model are grounded in the event data that sits underneath. I can implement, or we have implemented this in Neo4j, in a graph database system, Neo4j. And you can use Cypher Queries to construct event knowledge graphs, to aggregate event knowledge graphs, and there's tutorials available on how to do this. What most people do not realize is that most of the real-life data sets that we're using in the process mining community research, the BPI challenge data sets, are object-centric. So in fact, you can already start doing object-centric analysis, object-centric process mining research or analysis with the existing data. In order to facilitate that, we implemented the Python library, which we call PromG, that takes the event data in and uses a semantic description of the data that describes the objects, the activities, their relations based on the OSET standard that is being discussed in the process mining community, and transforms this raw data after importing into a graph, fully automated. You can also start object-centric analysis using the OCPA Python library, where you start from object-centric event logs. Also, there's many object-centric event logs available for the BPI challenge datasets. And the OCPA Python library already offers more analysis functionality than the PromG Python library. And then we will see in the future how things are developing. So now I want to take you further beyond object-centric process mining by having you shown how things work, and I can show you what you can do beyond object-centric process mining. And the first thing I want to show you is that you're not tied to analyzing business objects that are managed in your process. I can add the actor, the employee, the user, or the resource that's working in these processes also as an object. So almost all event data can, or almost all processes can record who is working in the activities. And if I use this attribute, the actor attribute, as an object or as an entity, I can add, for example, for the actor R1, an entity node. And as before, link all the events where R1 is involved to this entity node and then infer the directly follows path over these events. So now I see how R1 was going over multiple different objects and was working on them over time. If I do this for all the other actors as well, I get this network of how all the actors interact over the different objects. A look at this in real-life data, for example, like the BPI Challenge 2017 datasets, then we see this structure. And what's very interesting to see is that we see that objects are waiting for actors or resources. So you see this here where there's a new case starting. You see this here where there's an existing case running, and they're waiting for this actor to continue doing the next step. So that means when we think of process improvement, of understanding bottlenecks, we now have a new way of looking what keeps a process held up, not moving forward, and we can understand whether we need to redistribute, reprioritize how work gets distributed to the actors in my process in order to address a particular bottleneck. I can also aggregate the data with this actor perspective, because what we see in data is that an actor rarely just touches a single event, a single object once and then moves on. What we often see is that actors do multiple steps of a single object or of related objects. And we call this a task execution, right? One actor performs multiple consecutive actions on the same object. And if we detect all these subgraphs where actors are doing multiple consecutive steps, then you see all the tasks here in this data. And tasks have another structure on their own, because we, for example, see here that actor R4 is doing the same task of same steps, pack, shipment, and ship, consecutively in two different parts of the process, two different orders. So it's like batch processing by this actor. We can also observe batch processing here in this part, where we have receiving the supplier and then supply order and then unpacking the products multiple times. But interestingly, in the first execution of this batch, the actor gets interrupted, it interrupts the task, updates the invoice, and then they come back and continue the execution. So again, this gives a different understanding of how people work and what might hold up the flow in the process. We also see complex patterns in these interactions. We see that here two actors each performing the same kind of task consecutively, right? 5 executions of the same task, yellow task, by the first actor, and then 5 executions of the green task by the second actor. And they do this one after the other. So there's complex synchronization behavior happening in processes, and we can analyze them. And there's a very interesting paper and presentation by Bianca Baculari that explains how this can be analyzed. We can also use these task executions that we've identified to cluster, to aggregate information of how actors work. So if I take all the task executions that you've seen, these small sequences in these gray boxes, and I cluster the ones that are similar in the activities, then I get a local model of similar task executions. So I understand, okay, this is different ways of achieving the same thing. And this is a local model of actor behavior. It's not just one actor, it's many actors that can participate here. But it describes what one actor does from start to end on a particular case or on particular related objects before moving on to the next. And if I do this aggregation for all the task executions in my graph, then I can discover a new kind of process model that describes the interactions between actors on a global level. So each of these nodes contains such a small local model of task behavior, and the blue edges here describe how the different tasks are interacting. You can also analyze drifts in actor behavior, actors changing the way of work, changing the way of doing a particular task, preferring one variant over another. We can look at other kinds of objects. For example, in IT incident management, we're managing service components, hardware or software components. And there's multiple processes involved in incident management, the incident itself, the activity to explore the incident, interaction to investigate or work on the service component, and the change to update the service component. And the service component, that's not a process. It's the thing that's managed. It's a persistent entity that exists in the organization over time. And for example, if I model in an event knowledge graph the changes that are being done over the service components, then I see that many of the changes always touch the same set of service components, but there are some changes that are only done to specific service components, and also some changes are executed in different orders. Here's a different part of the same data set from BPI 14, and you see that there's fairly complex ways of how different service components are managed over changes. And we have not explored that so far. So I think there's a very interesting opportunity to also improve the analysis of such kinds of processes with the ideas of object-centric process mining. You can add an analysis of entire systems. So we've been doing lots of projects with Van der Lande. We're building baggage handling systems, and these baggage handling systems they transport bags to aircrafts, and they're not only transporting the bags, but they're using these yellow tubs where the bags are loaded in and then moved through the baggage handling system, which consists of a lot of equipment, which also has objects and entities that are subject to processes that are managed and controlled, and they're all interacting with each other. And what I want to show you now is an event knowledge graph that we've constructed for this kind of process. It integrates all the different parts of the system. And what you see here is in purple the layout of the system. So this is the physical connections, the physical points. And the purple edges are the directly follows path, the conveyor belts between these different points. What you see in yellow is these yellow tubs as they moved over the layout of the system along the conveyor belts. You see in blue and in orange the events of the process control that were looking were asking to receive yellow tubs at a particular location because they're needed to load bags into them, or to route yellow tubs into a particular direction of the system. And you also see in orange events that indicate when a particular part of the system was currently not accessible, for example, because there were already lots of yellow tubs in that particular part, and another yellow tub couldn't be routed there. So the part was out of service for this particular tub, and then the tub had to take a different route. So from this integration of all the data, you get to a completely different view on an entire system, and you could call this as a system fabric. You can use these event knowledge graphs also to extend it with further information, with context information like activities, locations, and information about on which types of objects activities work, and use this information to infer missing information. For example, if some events have not tracked a particular object, then you can use the context information to infer which object it was that an event was related to. And there's a paper by Avas-Webels on inferring missing entity identifiers using event knowledge graphs and context. So we've talked a lot about objects. Now, there's also relations in our data that we need to consider. So far, we try to ignore them, but they are there, and there are use cases where we need to look at relations. SAP ERP systems are a typical example where relations play an important role, because in the data model of SAP, well, we have different objects with headers and lines, and then all the events are recorded in these change tables. And an event in a change table always refers only to a single object. So we do not have relations recorded inside the events. And you can try to fix this through data extraction, but you can also do this in the event knowledge graph. We've done a case study in auditing where we modeled the data of an process in an event knowledge graph. We modeled the objects, but also the relations between the objects. So we have here a purchase order header, and we have a purchase order line item, and there's a parent-child relation between these two. And when we have a parent-child relation between two objects, then we can also study the interactions between these two objects. So we can order the events of the line item and the events of the header over time and study the directly follows path between both objects. So this is similar to the idea that we had before in artifact-centric process mining, where we kind of merge events of related objects, but now in the context of a well-understood data model. And so we can here analyze how line items relate to the header, but we can also analyze how objects on the of different kinds, for example, the purchase order line and an invoice line that receives the purchase order line, are related over time by also adding this directly follows relation. And if you want to know how to construct this relation, you can look at the chapter in the process mining handbook on process mining over multiple behavioral dimensions with event knowledge graphs. Now, these relations, also objects, they're not static. So far, when we talked about data, we always just had one single object node that exists or one relation that is there. But data gets changed, data gets updated. So we did a case study in configuration management and manufacturing of complex high-tech systems. And we modeled the changes to the configurations in an event knowledge graph. And one of the structures in this knowledge graph was that there are parts, physical parts, that are used in the construction of a particular machine that have to be part of a particular change release package for the change on that machine. And the information, whether that part is part of this release package, gets changed over time. So here I'm modeling that this object is part of that object as a relation that is materialized as a node. So this node here describes the part of relation from this object to that object. And then I have an event that adds this relation between these two objects. And I have another event that later on removes this relation and adds another relation between this object to another object. So I can model the changes of relations over time also in event knowledge graphs. Can also model changes to attributes. For example, the road traffic fines management process event log has a lot of attributes about traffic fines. So, for example, I have the attribute how much I have paid as a traffic offender. And initially, when the fine is created, I haven't paid anything, but I'm now modeling the attribute itself as a node with its value. Then I see after the first payment, I've paid 31.3 euros, and after the second payment, I've paid 42.71 euros. And in parallel, we see other attributes like here, the fine value itself, which was initially 31.3, which was the value that was paid, but later on a penalty was added, and that I didn't pay in full. So there's more ways of how we can extend event knowledge graphs for analysis. So what I showed you in this talk is that we can go out from the classical process thinking where we study one object and one flow into object-centric process thinking, where we analyze the behavior of multiple objects using object-centric event logs, object-centric process minings, event knowledge graphs, and they describe the execution fabric in a process. If we add, for example, the actors or other objects that exist far longer in time and that are kind of touched on by many different process executions, we can analyze all the flows in the process together, system usage, the resources, and we see a process fabric, the entire process of all executions together. And if we add knowledge about the system, we also get a system fabric that we can analyze. And the data exists. We have in each of these quadrants data available in form of event knowledge graphs or in form of object-centric event logs. And it's now time to start looking for new research questions, to address the research questions that are in these quadrants for discovery of descriptive process models, both local models that describe a small part or a global model, an end-to-end model. And we need both because these dynamics are so complex, but also predictive models or simulation models, now that there's more information available, can benefit from it. Conformance, understanding how well a model describes such a complex dynamics, but also enhancement, extending the data that we have with further domain knowledge to do inference, to analyze even better what's happening in processes. And above all of these, how the data, the objects, the relations change over time. And this data is available, so that means you can start researching today, you can start analyzing today using the OC-Petri library, which implements a lot of process mining techniques already, or our new PromG library, which helps to automatically construct these event knowledge graphs for several BPI challenge datasets. And both Python libraries also allow you to script analysis for object-centric processes. Thank you very much for listening, and I hope this gives you inspiration for your next steps as a process mining analyst or as a BPM researcher. Thank you.